In this lesson, we will define Le Chatelier's principle and predict how the change in amounts of substances, temperature, or pressure will affect the amounts of reactants and products present at equilibrium. Le Chatelier's principle states that when a reaction at equilibrium is disturbed, the system will respond to minimize the disturbance. In other words, when we have some kind of a change, the reaction will spontaneously try to undo whatever it is we've done to the system. We will look at this in terms of either adding or removing a substance, which could be either a reactant or a product, changes in temperature, increasing or decreasing, as well as changes in volume, which lead to a change in pressure. One way to think about Le Chatelier's principle is to think about an elevator. Imagine that you are on an elevator and you walk in and you're the only person there. You press that you're going to the 10th floor and you stand in the middle of the elevator. On the second floor, someone else gets on, they press their button, and you notice that they don't stand immediately next to you. In fact, they'll stand on one side and you'll probably shift to the other side so that you're more spread out. On the next floor, someone else gets on. Everybody rearranges slightly to spread around the space so that no one is standing inordinately close to someone else. This is what's going on with Le Chatelier's principle. There is some stress to the system, such as adding additional reactant, and the system responds to minimize that disturbance. This is the same as someone else getting on the elevator and everyone shifting positions to minimize that disturbance. As we talk about Le Chatelier's principle, we will use the term shift for a reaction. So imagine we have the reaction A going to B, where we have a system at equilibrium. We know this is an equilibrium reaction because of the use of the equilibrium arrow. And we're going to describe two different processes that can happen in a reaction as a response to a disturbance in the system. The system can shift right, which means it's going to shift towards forming more products, and we can also describe this as favoring the products. In that case, we increase the amount of B, which is on the right side of the reaction or on the product side of the reaction, and we will decrease the amount of A, which is on the left side or the reactant side of the reaction. Or we will shift left towards our reactants, which are on the left side. We can also describe this as favoring the reactants. In this case, we will increase the amount of A and decrease the amount of B. Let's look at an example where we're changing the amount of a substance. We have a balanced chemical equation, and we also have the enthalpy. We won't use that when we're looking at the amount of reactants, but that will become important when we look at changes in temperature. Let's look at adding SO3, which is a reactant on the left side of the equation. First, we need to think about the equilibrium constant expression, which tells us about the concentration of the products over the concentration of the reactants. We've added additional SO3, so we have more reactants with the same amount of products. As a result, the ratio is now too low. We are no longer at equilibrium. According to Le Chatelier's principle, the system will respond to minimize that disturbance or to minimize the addition of SO3. Therefore, we will see a shift to the right or the formation of more products, and this will decrease the amount of reactant, so decrease the amount of SO3, and increase the amount of SO2 and O2. As we increase the amount of products and decrease the amount of reactants, we will change the value of Q, our reaction quotient, so that it returns to the value of K, our equilibrium constant. Next, let's look at what happens when we add SO2. SO2 is a product, so the value in our numerator is going to increase, while the value in the denominator is going to stay the same. As a result of that, the ratio is going to be too high. The system needs to respond in a way to lower that ratio till it gets back to the value of K. Therefore, we will shift to the left, which will increase the amount of reactants and will decrease the amount of products. By increasing the denominator and decreasing the numerator, The value of Q will decrease until it's equal to K, and so our ratio will return to its equilibrium value. Next, we'll look at removing SO3, which is a reactant. This also results in a ratio that is too high. Therefore, we need to shift to the left to return to equilibrium, and this will increase the amount of reactants and decrease the products. If we remove a product, such as SO2, we will have a ratio that is too low. Therefore, we need to shift to the right to increase the amount of products and decrease the amount of reactants. When we have multiple reactants or products, we will see the same effect regardless of which reactant or product we add or remove. In this case, we used examples of adding SO2 and removing O2. We would also see the same effect if we added O2 or removed SO2. Now let's look at an example where we change the temperature. In this case, the enthalpy will become important. Notice that we have a positive value for our enthalpy, which tells us that we have an endothermic reaction, so heat energy is going into the system, and so we can treat heat as a reactant. If we increase the temperature, we are adding heat. This is the same thing as adding any other reactant because we've already determined that heat is a reactant. As a result, the reaction will shift to the right, and this will lead to a decrease in the amount of heat because some of that heat will be consumed in order for the reaction to shift to the right. If we decrease the temperature for an endothermic system, we are removing heat, so that's the same as removing a reactant. As a result, the reaction will shift to the left to increase the amount of heat present. When looking at adding or removing products, the shifting left or right happens exactly the same way. However, when we look at changing temperature, it will depend on whether or not the system is endothermic or exothermic. Next, we will look at a change in volume. Again, the enthalpy is given here, but it is not relevant to this particular scenario. When we look at the left side of the reaction, we see that we have 2 moles of gas. We know we have 2 moles of gas because there's a 2 in front of the SO3, which represents moles, and the G after the substance, which represents gas. So we have 2 moles of gas on the left side of the equation, and on the right side of the equation, we have 3 moles of gas. When we look at an increase or decrease in volume, we have to consider the moles of gas on either the reactant or product side of the equation. When we increase the volume, we are causing a decrease in pressure because now the same amount of molecules are confined in a smaller space. To minimize that decrease in pressure, we need to do something that will cause an increase in pressure. As a result, we will favor the side of the reaction that has more moles of gas, because more moles of gas will result in an increase in pressure. So this reaction will shift to the right with an increase in volume. When we decrease the volume, we see an increase in pressure. To respond to that, we will favor the side with fewer moles of gas, because fewer moles of gas will lower the pressure inside the container, and this will decrease the pressure, so it's a direct response to the decrease in volume, which increased the pressure. As a result, for this reaction, we will shift the reaction to the left to form more reactants and less products. As with changes in temperature related to enthalpy, these changes also depend on the moles of gas in the reaction. So there is no hard and fast rule of shifting left or right with decreases or increases in volume.